Oh, this is a good one. We've got some of the Manulife SRE gang talking about how they implemented some efficiencies on their platform to get some amazing results. But spoiler alert, they saved a bunch of money. So tune in and listen to how they did that.
All right. Hello, everyone, and thanks for tuning in. My name is David Wu. I am from VMware Tanzu Labs. And with me today, I have David Filippelli and Alvin Koch from Manulife. And together, we're going to present our work on how we unlocked platform efficiency and reliability while saving over $730,000. But before we begin, I have to make a quick correction to the title. We actually didn't save $730,000. We saved over $1 million. So that's a bit of a bonus in today's presentation. So before we dive in, let's just talk about the agenda. So we'll kick it off with PCF at Manulife. What does it look like? Then we'll go into efficiency versus reliability. And then we'll look at the activities that we did to improve the efficiency and reliability. And then we'll conclude with tallying the savings. Finally, we'll show the references, acknowledgements, and Q&A. All right, I'll hand it over to David.
Thanks, David. So just to give you a little bit of information about Manulife, we have 7 PCF foundations across North America and Asia, roughly 8,000 AIs, and about 540 Diego cells across all the foundations as well. So essentially the problem statement is how could we improve the efficiency and reliability of our platform and at the same time saving some money.
All right, thanks, David. So what are we trying to achieve? So efficiency, we're trying to make the platform run better and therefore make the platform engineers and their bosses life easier. So some of the things we want to look at is optimizing the resources used. We want to reduce the cost and time to do things. We want to improve monitoring strategies so that we pick up problems before the developers do. Now, reliability, this is one of the key ingredients to an exceptional customer service platform. So we want to look at increasing application uptime, increase service availability, and improve recovery point of objective. So here are the activities that we worked on to do that. So we'll look at the Diego cell scheduler, and then we'll look at TAS internal blob store to external blob store. Then we'll look at changing and tuning Diego cell VM types, and then finally foundation configuration tuning. So I'll hand it over to David.
Thanks. So at Manulife, we basically developers actually developed a scheduler app. And essentially it allows developers to self-serve and subscribe to apps and what time of the day and week they want to stop their apps. So the incentive to the developers was to save on costs on chargebacks. Next slide, David. And because of that came along the Diego cell scheduler. So we noticed a trend in dev and sandbox environments. They were not fully utilized on the weekends and Friday evenings from Friday to Monday. And this cost was incurred both at the app level and the platform level. So we decided to capitalize on some platform savings as well. And how we did that, we essentially created a concourse pipeline to query the Diego cells memory utilization after the apps were stopped to determine how many Diego cells to scale down by. And this was reverted as well on the Monday morning to the beginning values.
All right, thanks. So now I'll pass it over to Alvin to talk about internal blob store to external blob store.
Hi, everyone, and thank you, David. So I'm going to briefly walk you through how we improve the efficiency and reliability of our Tanzu application service by switching the internal blob store to an external blob store. Previously, we had an NFS VM, which was acting as the internal blob store. And we realized that the cost of the VM, both the compute and storage cost was more than the cost of using an Azure blob store. So we decided to switch, and what this allowed us to do was decrease the platform upgrade times while also bumping up availability. The NFS VM was a single point of failure. It was one VM. It wasn't HA, and it had a pretty big persistent disk, which led to long upgrade / backup times, which also in turn led to developer outages and potential issues with auto scaling and healing. So by making the switch, we're able to decrease the backup time and reduce the outage, which was caused by the cloud controller lock. For some times in our testing in Sandbox, for example, the backup usually used to take 3 hours, and the lock on the cloud controller was around an hour and 15 minutes. We're able to drop that down to 13 minutes and 1 minute for the cloud controller lock. So essentially, we eliminated the outage, which allowed us to do more backups and ultimately increase our recovery point objective, our RPO. Can we go to the next slide, please? So before we made the switchover, we had to do some prep work. We first created the Blob store in Azure and created 4 containers, which basically mimic the internal directory of the NFS VM. We also had to set up service endpoints to speed up access to the Blob to ensure that traffic is not traveling over the public internet, but goes through the Azure backbone. And we also had to set up some firewall rules to ensure that our cloud controller could talk to our Windows Diego cells and pull in build packs. Can we go into the next animation, please? So 5 days before the cutover, we did our first migration. We basically used our clone to transfer the Blob objects, which is an open source copy utility. And while we're doing this first copy, we checked for routing issues, and we were able to benchmark the transfer speeds. We also did another migration a day before the actual cutover to copy over the deltas and make sure that any new blobs that were added to the NFS were also copied to Azure. And then we performed the cutover. Can we go to the next slide? So on the day of the cutover, we first had to baseline our app performance. So we basically timed CF pushes using candidate apps with different build packs on both Windows and Linux to see how long it took to push to the internal Blob store. When we had that baseline down, we locked down the cloud controller so that no more data could be pushed to the internal NFS using the CFCLI. And then we did the final copy, which basically synced up the 2 Blob stores. And after that, we took a snapshot of the NFS VM to make sure that we always had a backup. And when that was done, we did the switchover and applied changes in Ops Manager to point the task to the Azure Blob. Following that, we also run a second baseline test to see if the times were comparable to the first and to see if there's any network issues. And when we were satisfied with that, we basically unlocked the cloud controller and called it done. So that's how we improved reliability and also saved costs. Over to you, David.
All right, thanks so much. All right, let's look at changing and tuning Diego cells. So what do we want to achieve? We want to optimize the utilization of resources such as the memory and the disk. So we had a bunch of apps that's not writing to disk, that's essentially wasting. So we looked at the ESV3 series on Azure, which was memory optimized VMs and less disk space. By default, TAS packages DSV2, and these cost more than the ESV3 VMs. We also want to look at how we can actually reduce the disk space usage. More on this a bit later. Now, when we switch over to ESV3, the amount of memory on these VMs is slightly larger than DSV2. So this means that you can fit more application instances. And therefore, this leads to a decrease in the VM count. Now, you can increase the memory, but we don't recommend doing that. Secondly, improving reliability through tuning. We ensure that there's enough resources to support the current needs and the future growth. So what questions do we want to know answers to? And we need quantifiable answers. So here are the questions. How many Diego cells do I need to fit X application instances? Are we under-provisioned or are we over-provisioned, and is it the right amount? What's the right amount of minimum disk that we need per cell? So in Azure, we found that if you used 129 gigabytes, you'll be charged at the 256 gigabyte tier. Now, other information we need. So we want to know what else is running on the cells. You know, what Bosch add-ons do you have, and how much memory do they need? For example, CLAM antivirus. Then we want to know how many AIs are there on the foundation. What's the average memory use per AI and the disk quota? All this you can grab from the CF API. This will give you a snapshot. There's a script from Rakuten that can grab a table output, and you'll be able to import it to Excel and get the averages. All right, so now we got that data. Now, how do we use that data to model our capacity planning? Now, we can go through the capacity behavior through the TAS container and architecture docs, but we have a worksheet here that can help you out. So all you need to do is get that raw AI memory data, get the averages of it, and this will be in megabytes. And you just get those averages divided by 1024 to give you gigabytes, and you input them here at this point in the spreadsheet. Now, once you do that, this will give you a bunch of statistics. And the most interesting ones will be obviously the minimum disk space and the Diego cells needed. Now, with this capacity information, you can build capacity monitoring dashboards and do alerts. You'll be able to do simulations as well. So like, for example, what if tomorrow 25% of my app instances switch to higher disk use? Do I need more Diego cells? This is good information to know about how your performance and how your foundation is being used. So there are additional things to consider. So for on-prem and availability zone customers, you want to make sure that you have at least 1 on n% of extra memory and disk to cover one AZ failure. So for example, a 3 AZ, if one of them falls over, you want to make sure that there's enough memory and disk so Bosch can recreate those VMs in the other remaining 2 AZs. So you also want to factor in additional resources per cell to reserve for add-ons and any future growth. Now, in Manulife, we used around about 20%. This can be treated as your warning level in your monitoring process. And we also spoke earlier about increasing memory, and you can decrease the number of VMs and increase app density and pack more application instances. But we don't recommend doing this too much because this will lead to longer evacuation times, longer recovery, longer VM updates. Now, this can also hinder application performance because CPU share is based off the AI memory. Okay, let's get into changing the VM type. So what do we need? So to change VM type, you want to have historical metrics for your CPU, memory, and disk bandwidth. So preferably if you have over 30 days and you know when there's seasonal times of heavy usage, your IaaS should be able to give you this information. But if you don't have enough data, what can you do? We do have this blue-green algorithm that we'll show later that you might be able to use. All right, another thing you want to consider is, does this VM type support your needs? So look at the VM type and know what the maximum is. What's the maximum CPU load, disk IOPS, and memory, and compare that to the heavy usage metrics that you have on your foundation and see if they make sense. But we also recommend spinning up VMs and just writing out tests and just make sure it works. This is a bit of a sanity check on our end to make sure that there's nothing strange happening. So how do we now implement this? So in Ops Manager, it's pretty straightforward. You go into the task tile, jobs, and then go to the down drop list and change the VM type. If the VM type is not there, you'll need to use some sort of Opsman core to actually change and add that in. For Opsman 2.10.3, they did support the new generation of Azure VM types, but without availability sets. In our situation, we were using availability sets. We weren't able to use the ESV3 because the availability sets were sitting in old Azure hardware clusters. Now, in our situation, in order to switch that, we had to have only one VM in the availability set. So that means that we have to scale down a TAS foundation, say with over 100 VMs down to 1 before we can switch it over. Now, this probably isn't tolerable in our situation and in most other organizations as well, because that's going to lead to downtime. So we had to come up with a way to get around this. This is where we kind of developed a switchover algorithm. But before using this algorithm, we have to make sure that we have enough VM quotas and our subnets have enough capacity. You want at least double your current TAS to do this. Also, you want to make sure the firewall is set up. We just use the same subnet as existing Diego cells to create new firewalls to avoid creating one. Okay, so here is our algorithm. So it involves using isolation segments. If you already have an existing one, you just replicate the tile and just give it a unique name. You'll want to leave the segment name blank to extend the pool of Diego cells, TAS Diego cells. So here's an example. So first off, we start off with our TAS Diego cells running with the DSV2. The blue are the applications running inside those VMs. Then we set up the isolation segment. We scale up all the Diego cells with the ESV3. And at this point, there's no apps running inside it. Then we start scaling down the TAS Diego cells. And as we do this, apps are evacuated and then relaunched on the isolation segment. Now, what we found the first time we ran this was that there's a max in flight for the Diego cells. And so going from 100 to say 10 VMs resulted in a max in flight of 1 VM, which took a long time, like almost 12 hours plus. We kind of came back again and looked at what we can do. And we can adjust the max in flight. Now, you can do that, just be aware and monitor your BBS load. Now it would come to a point where your TAS has only one Diego cell, but you notice you can't change this to 0. But that's okay, because we only need 1 in order to switch it over. So we switch it over, and all the apps get evacuated and relaunched into the isolation segment. Now we scale up the TAS with the ESP3 VMs and go in reverse and scale down the isolation segment down to 0. And while you do that, your apps are going to be relaunched inside the TAS ESP3. Once it's done, just delete the isolation segment timer, and that's it. All right, I'll pass it over to David now to talk about foundation configuration tuning.
Thank you. So what we're trying to achieve here is basically optimize utilization of VM resources, decreasing VM count for overutilized resources, and increasing VM count for better platform health and high availability. Next slide. So here, it essentially was around getting your monitoring ready. We use the metrics, the KPI metrics from VMware to allow us to look into these points, the cloud controller, UAA, logerator, and other items listed to allow us to get that insight. Next slide. So what we did is we tabled out the changes. It allows you to get that high-level overview and see at the bigger picture what you have, how many you have, VM types, and where the discrepancies lie. Next slide. So the general VM metrics, we looked at CPU, memory, and persistent disk. Next slide. Logerator was a component that we actually found ourselves, we were ratioed incorrectly, where we had a one-to-one mapping after determining what the appropriate ratio should be, which should be a 2 to 1 to 1. We made those changes and it allowed us to save some additional cost and tuning as well. Next slide. This is just a dashboard that we put together with all those metrics to allow us to visually see if we were just dropping any messages, the performance of the components, and where we had to make changes. Next slide. For the cloud controller, we looked at as well CPU, memory, and persistent disk. And we were looking at the data that was coming in to be able to determine if we could scale down or up to utilize our resources better. Next slide. Once again, it's another dashboard that we put together with the metrics around cloud controller to give us that insight and visibility into how it was performing after our changes and where we need to make additional tweaks. Next slide. So I guess when we did all this, we said, well, how much did we actually save? So Diego cell scheduling, we saved roughly 21,500 per year, and that's about 30 VMs we delete every weekend and we recreate every Monday morning in our North America foundation. Switching Blob stored external, that was about 40,000 per year. And the big one was switching the Diego cell VM type. So that was the $1 million where we saw the biggest bang to get a big return on this investment. And at the end, we ended up saving the total of 1,060,000. Thanks to everyone's help, we were able to achieve success.
All right, thank you. And so here I've got the references. And most importantly, we want to thank everyone here that came in to attend. But more importantly, we want to thank the following people for their involvement and efforts to make things happen. All right, so questions and answers.
All right, well, thank you so much. I liked how you pivoted to $1 million. Yeah, I know. The joke's been overdone, but I had to. I had to. Anyway, please join the gang for some chat on the Slack channel. They probably have lots more wisdom to impart. So thanks again for sharing your journey, gang, and looking forward to hearing more.